Right. Hello, everyone. We'll, I guess, get to the review in about 5 minutes. Until then, sit back, relax, and yeah, sit tight.
Sir,
Yes.
I have a question. Is there any way that the midterm could be pushed to Friday's class?
No. I'm sorry. It's out of my hands. The invigilators and everything were coordinated last week, so at this point, I cannot, like, if I
Oh,
wanted
sorry, you're
to.
frozen. I can't hear you.
Oh, my internet connection. Hang on a sec. Uh, yeah, no. Short answer is no. Long answer is it's out of my hands. I can't change it.
Okay, thank you.
Is it possible to move the next exam to the Friday class though?
What's that?
Like the next midterm, because we've got chemistry and waves in the same week,
The one that's in
and chemistry's on the
April?
Monday.
Yeah.
Yeah. So like, if is it possible to like try and arrange that we have that one on the Friday?
Remind me. So that one is what, on April? What is it? April 23rd, April 10th.
I have no clue. I just know the next one's on the same. It's also on a Wednesday.
Oh my gosh! See, this is. What's the bio of the chem teacher? See, we have a shared
April
calendar
21st.
where we put our tentative exam dates, and the whole point of that calendar is so that teachers don't overlap. But clearly, I'm the only one using it because whenever I put a test down, all of a sudden, there's another teacher has it the same day. Let me look at the calendar right now. Yeah, that's totally fine with me. I mean, oh wait, no, we're looking at. So Wednesday 21st. Okay, so Monday 19th, yeah, you have the organic 1 midterm, and 9 a.m. you have the. We push it to a Friday. Okay, I'm going to again that I'll check. I'll ask the school again. That at the end of the day, that is not in my hands entirely, but I will ask and I will try to get it to happen on a Friday if I can.
Thank you very much. Just seeing if it's possible. Thank you.
Yeah, no worries. Yeah, I'm gonna write that down so we can get a hold of this desk soon enough. All right. Well, where's my? That would be everything. Okay. All right. So yeah, no, we're gonna go over everything today. All right. Hey everyone. Hope you're doing well. I know we're like entering midterm season and things can get a little stressful. So I finished writing the midterm yesterday, and then I took it. It took me 40 minutes to finish it, and considering that you have like 2.5 times that time, I think you'll find that it's super comfortable to finish it in 2.5 hours. It's meant to be a 2-hour midterm, so the extra half hour will take some of the edge off. And what did it end up being? So there is going to be like 3 short answer questions. One of them is a true or false, where like you'll just be asked to like look at 4 different statements, say if they're true or false, and explain why in like 1 sentence. And there is 6 long answer questions where you'll be expected to show all your work. You get more marks for showing everything leading up to the final answer than you'll get for just stating the correct final answer, right? So if your whole work looks good and then for whatever reason your final answer is not quite correct, well, you're getting pretty much most all the marks. As long as, of course, as you keep units in your answers and everything looks neat. I'll talk more about that as we go through. Basically, the chapters that we covered were 15 through 18, depending on which textbook you have, that may have gotten condensed into 3 chapters. Either way, though, the general theme of all of them is this periodic motion, this cyclical propagation or movement of either some kind of pendulum or physical object, or simply a way of moving through space, whether that's sound or just vibrations on a guitar string. So even though at first it does seem like there's a lot of stuff, really it all comes back to this idea of cyclical motion. So the more you practice, the more you realize how the chapters really are harmony. And that's a pun totally intended. Anyways, I'm just gonna go through some of the slides that we had for the past few chapters. Let me make sure I don't have the midterm open in the wrong tab. Where am I? Okay. So the first chapter we did was, before getting into the whole waves thing, we started with a more down-to-earth example of cyclical motion, which is just springs and blocks and also pendulums. And the idea is that an object tied to a string, it can undergo a harmonic motion due to the fact that the farther it's pulled or compressed from its equilibrium position, there will be a restoring force that sends it back to equilibrium. Now, anytime we talk about equilibrium position, it's always going to be the same idea. It's wherever the part of the wave or the pendulum or the block is where it would like to be if it was undisturbed. In the case of the spring block system, if you leave it alone, then wherever that block sits when it's left alone is equilibrium position. The reason why it undergoes motion, though, is that when you pull it, the restoring force pushes it back, but it always overshoots if there's no friction. So it gets pulled back way past equilibrium, and now it gets compressed. When it gets compressed, the restoring force wants to push it back to the right, which ends up stretching it, which sends it back to the left, and so forth and so on. Now we learned that in the real world, though, frictional forces slow down the block and cause damping, which sends it to its equilibrium position either really fast or really slowly. But we don't have to worry too much about that, just understanding that in this case, the only force present is really the restoring force, because we're assuming there's no friction. And the restoring force then is some function of the displacement from equilibrium position and some constant called the spring constant K. Now, the idea is that stiffer a spring is, the more it wants to return to equilibrium. So a stiffer spring will have a lot larger spring constant, creating a stronger restoring force. You'll note then that the acceleration of restoring force can be found using Newton's second law, which means that if you know the block's mass, you can then find the acceleration at any point in its displacement. We're also assuming that the spring is massless. All the mass is on the block. Same thing with the pendulum. So the cool thing is that when it undergoes simple harmonic motion, the spring block system can be defined using trigonometric functions. Its position can be done with either a cos or a sine function, since it moves from one side to the other over and over again. You can use a cos function with a term accounting for its frequency of oscillation, that's omega, and also a term for its amplitude of oscillations, that's A. And
I have a question.
yeah.
But the thing about it is, isn't taking the derivative of a function going to give you the speed, and then taking the second derivative, the acceleration? Or is that just my imagination?
Yeah, that's true. That's how you get the acceleration and position of the.
Okay, would that be a reasonable question to ask us, like on the test? Would you include derivatives?
No.
So there's no derivatives on the test.
No, as a matter of fact, you can do the whole test without using a single sine or cos function. So
Yeah, well, I also know that there's like other formulas that you can equate to give you the same thing.
Yeah, that's true.
So I understand what you're saying because I've looked at like a lot of questions. Thank you.
No worries. Right, so the equation here is a very, very general form of the. This is a very general form. This will tell you the position at any point in time of the block. So the phase factor here that you'll see in waves as well, that just accounts for the starting conditions, because the starting conditions, right, that's at some starting point 0. So all that's left is the phase factor inside. And if you start at your equilibrium position, then your phi is something like pi over 2. If you start at your amplitude, so x starts at its maximum displacement, and the phase factor is probably going to be something that maximizes the cos function, like 2 pi or 0, because right that way, because a cos of 2 pi gives you 1, which, here, let me make some room. Right, you'll have a cos 2 pi, which just give you a. So that's what the phase factor is for. Just it's there to specify where you're at the starting point. So you can also, yeah, like we said, we can describe the speed and acceleration of the block. You'll note then that the maximum speed and maximum acceleration comes from finding the maximum of the respective functions. And the term here, omega, that's a property of the spring block system. That's your angular speed, right? Which you've seen though for like waves on a string, that the speed of the wave was the tension over the linear mass density. And for sound waves, the ratio was, I believe it was the bulk modulus over the density. So all these formulas have something in common, which is a ratio of a term that kind of measures the stiffness of the medium, right? That's the tension on the string, the spring constant, or the modulus of the medium which air moves through. And on the denominator, there's a term that measures the kind of like inertia of the system. So there's a term here for the mass density, a term here for the mass of the spring, and a mass here for the density of the gas. So then angular frequency is always going to be a property of the medium, which is why no matter what the wave is, the speed is constant in the medium. The interesting thing about the spring block system, right, is that the velocity and the acceleration are out of phase with each other, since as the block oscillates left and right, it gains speed the closer it is to equilibrium, but then it loses that speed as it gets stretched and compressed, since the restoring force deaccelerates it, which means that the acceleration reaches a maximum or a minimum at points of max displacement, while the speed reaches its maximum value passing through equilibrium. And it becomes zero at when it reaches max amplitude. So you see here, when your position's at the amplitude, your speed's zero and your acceleration's maximized pointing to the right. So we talked about period, very important. It's how many seconds it takes for one cycle to be completed. A cycle, whether it's a wave or a pendulum or a spring block, is just how long it takes to go back to what you started doing at the very beginning. If you look at a graph of position versus time, then the period would just be the distance between two peaks. In this case, right, you're saying that if you start from here, x is at its max amplitude, goes to equilibrium, goes to negative amplitude, goes through equilibrium again, and now goes back to max amplitude and then repeats. So however much time passed from here to here is one cycle. And there's this relationship that you can derive, which is in your formula sheet, between the angular frequency, which is the property of the medium, and your period. So they're inversely proportional. The faster something is, the shorter its period, because it takes less time to complete a cycle. And then frequency is proportional to the angular frequency. It's a linear measurement of how fast a cycle is completed. And the units of that is the hertz. So for a spring, you can also know its period and the frequency if you know its angular frequency. And again, it's a property of the medium. It doesn't depend on the amplitude of the it doesn't depend on the amplitude of displacement, which means it doesn't depend on how much energy the system has by virtue of being stretched and compressed. So here's a graph from the open physics textbook, which I put in your course outline. It's an open source physics textbook, which pretty much covers the same material as the survey book and has some really nice graphs, and it's all free. So this is just showing you as the spring moves from a position at its max amplitude, as its max stretch, it shows you how the restoring force acts. And right at max stretch, the restoring force pushes it to the left. There's no speed here. But then you shoot back to equilibrium and you have reached your max speed pointing to the left. That's just now you're moving towards the left, you're moving towards compression. Note that there's no restoring force at this point. Then you get fully compressed, the restoring force pushes you back and you get pushed back to equilibrium. And once you reach this position, you have completed one full cycle. Okay, nice. So this is a description of the movement, assuming you start off from max displacement of this spring block system over the course of a period and a half. Note that it takes a quarter of the period to reach equilibrium, half a period to go to negative displacement, 3/4 of a period to go through equilibrium again, and then your full period once you reach max amplitude. So if you started measuring from passing equilibrium So at this point here, we start measuring the clock from here. You'll note that it takes half a period between reaching equilibrium. So if say you start the clock here, it would take a quarter of your period to get to here and half your period to get here. So overall then, the block passes equilibrium. The time it takes for the block to pass equilibrium is equal to half the period of motion. And here's just showing you the idea of how position changes over the course of a period. The graph on the right is showing you how you collect data yourself. If you build your own spring system and you're able to record pretty precisely what the position is, you actually do get a sinusoidal shape. And finally, because the spring has potential energy, you can measure its kinetic energy depending on the position of the spring, but due to conservation of energy, it always adds up to a total amount. So the potential energy is proportional to the square of its displacement, and the kinetic energy is just the one you've seen in kinematics, proportional to the square of the speed and the mass of the block. So as you move through in a cycle, there's an exchange between potential and kinetic energy. When you pass equilibrium, that maximizes kinetic energy, but at points of max displacement, A and minus A, you have no kinetic energy since you're briefly not moving, but you have all of your energy is now potential. So if you were to graph the total energy, the kinetic energy, and the potential energy as a function of time, you'll see that over the course of one period of motion, assuming you start off from max displacement, you're starting then with a maximum potential energy, which drops to 0 when you pass equilibrium at a quarter of the period, which gets maximized again halfway through the period when you're fully compressed. And then you pass equilibrium again, and then there you go. Kinetic energy builds up as you pass equilibrium, reach max speed, drops to 0 at full compression, back again to max at equilibrium, and then back to 0 as you go back to your max stretch. Your total energy, of course, remains constant. And here on the left, you can see what the position looks like over time and what the velocity looks like over time. Here is when you're moving through equilibrium. It's negative since you're moving to the left. Here we're moving through equilibrium again, but this time you're stretching, so you're moving to the right, so it's positive. If you just graph your energies as a function of position, you get this cool parabola. So you can kind of see how the kinetic energy in red increases towards 0 and decreases towards the amplitudes. And the potential energy is upside down, since when you reach the equilibrium, your potential energy is 0. And if you add them together, right, you get E total. The sum of the two always gives you E total. So the total energy, by the way, if you know your amplitude oscillations, and your total energy will always be this. And at any point in your displacement, you can calculate the energy. If you know the speed, spring constant, mass, and position of the particle, then you can calculate the potential and kinetic energies respectively. And you can actually, with this formula, you can actually get a formula for the speed of the particle at some particular point in time if you know the angular frequency, the amplitude, and what position you're at that point in time. So it's a pretty neat formula. So it's another graph kind of showing you what the different energy distribution is. So here's all potential, here it's all kinetic, here's all potential again, here's kinetic since you're passing equilibrium, and then here you're fully stretched again, so it's all kinetic, it's all potential, I mean. And of course you measure energy in joules. Pendulums. So, by the way, this part right here, the circle here, this is called the bob of the pendulum. Define that now. And a pendulum can be modeled like a spring block system in the sense that its motion can be defined as periodic and simple harmonic, with the assumption that the angle of oscillation is small. In this case, we also assume that it's a simple pendulum, so all its mass is in the bob, and what you end up with is a formula for the restoring force that's based on the gravity making it swing. So your angular displacement and your period look a bit different, since now you're looking at properties of the pendulum and not a spring block system. But then with the small angle approximation, if you know for sure that the pendulum is swinging through a small angle, less than 10 degrees, then you can find the angular frequency of its oscillations. Again, no friction or anything, just swinging back and forth. Its angular frequency depends on the force of gravity and the length of the pendulum. And again, the definitions for period and angular frequency and linear frequency are all connected. So if you know one, you know all of them. So the period of the pendulum then is 2 pi L over G. So the longer a stick is, the longer it takes to swing through. And now a period, again, it's always measuring a cycle. For a pendulum, a full cycle is however long it takes to go back to its starting position. So if it starts from maximum angular displacement, half a period gets it to the other side, another half period gets it back to origin. And also, like this spring block system, it passes equilibrium twice at a time equal to half a period. And you can also describe the position using angles, if you so desire. And the position formula again looks like the one for the spring block system, but now again, there's a maximum angle of displacement, it's not an amplitude anymore. None, yeah, so here it's looking with the period. All right. Yeah, so don't worry about complicated pendulums. Don't worry about damped or forced oscillators. That's what I'm gonna say. Yeah, the most important thing is understanding, right, how energy is shifted from one to the other over the course of a period, and also how the spring block moves and what its velocity and acceleration is over a whole cycle. Just understanding that will get you pretty far. So having established a simple oscillator like it, where it's just one thing, one block moving left and right, or one pendulum moving left and right, we now take this idea of cyclical motion and apply it to something that's a bit more broad, which is just waves in general.
Sir, I have a question.
Yeah.
Because you gave us a lot of conceptual questions, and I just wondered why, if there's only one actual conceptual question on the test.
There is?
Well, you told me that in an email. I don't know.
Oh, that's a question. Okay, I don't recall. Okay, if I did, I apologize. There's definitely more than one. There's definitely more than one conceptual question. Yeah, no, there's the question.
What I mean by saying that though is like, is it just gonna be like, questions about logic, or is there actually gonna be math on the test?
No, yeah. So the short answer questions will be more conceptual, just understanding the sort of the main ideas of each topic. But the long answer questions, though, there will definitely be math with perhaps, say, if a long answer question has 3 parts, it's entirely possible that part C will be conceptual, like you explaining why you got your results in part A and B. So long answer questions will be mostly math, with perhaps one part checking your conceptual understanding of what the topic of the question is about.
Okay, perfect.
the reason why I put up so many conceptual questions is because I think on some level that's going to get you farther, like in your understanding of the topic, than doing like, say, the same sort of math problem multiple times. I think like by thinking a lot of what was actually happening conceptually, it gives you a better idea of the topics and you see how they relate together. Because a lot of this I find is can be very sort of esoteric if we don't really, if we just kind of read the textbook all the time, kind of get lost in the technical definitions. So I wanted to get you to think more about things and how they might be in the real world as conceptual questions. Speaking of which, waves, we talked about two types, but for these chapters, we only dealt with mechanical waves. That's everything that propagates in a medium. So nothing like an electromagnetic wave, which we're going to deal with later, chapters 35 and beyond, which are their own thing. They don't need a medium to propagate. So a wave can be anything, just basically some pulse being sent through the medium that carries energy. And the idea is that it's easy to generate a wave. Every time we talk, we're making sound waves. We're just disturbing the medium in some way. Every time we play guitar, we make waves. So anytime anything's vibrating, that's a wave. So this is a wave, just a pulse passing through a hose. If you ever do gardening, right, sometimes you have to like untangle the hose. So what do? You just kind of swing it and then it kind of untangles. The most basic example is just this. And note that, right, like the hose is not moving. No part of the hose is actually moving left and right. They get disturbed for a little bit. They race up and then back down, but that's it. The wave keeps going without moving the medium itself. So the first waves we talked about were transverse, and these just make the medium move perpendicular. So if the wave's moving left to right, the transverse wave will make the medium jiggle up and down. The longitudinal wave makes the medium jiggle left and right in the same direction as propagation. So that's kind of like pulling on a slinky, or that's a sound wave. So the particles compress and stretch like an accordion as the pulse moves through it. And here's this wonderful GIF. So you can kind of see, right, how like there's this like pulse of compression in the slinky that's here, that's moving to the right. And in the transverse wave, the pulse is moving to the right, but the disturbance, the hose is shaking up and down. And you can see by the mark on the slinky, on the hose, that it's not actually moving to the left or the right. It's just kind of briefly being shaken up and then down as the wave passes through it. And yeah, wave functions is the way that you can describe a wave by either specifying its position or its point in time, or both. Because transverse waves displace the medium vertically, what the wave function does is it tells you what the vertical position of the wave is at any point in time and at any physical point along the wave. So if you specify a particular point, let's say the hose right here, this yellow point in the hose, and you're sending cyclical sinusoidal pulses through it, if you graph the position of this part of the hose versus time, you actually get a sinusoidal wave. So sending a sinusoidal pulse through a medium makes every part of the medium move in a sinusoidal pattern. That's pretty cool. As a matter of fact, when you send sinusoidal pulses through, every point on the medium moves in simple harmonic motion. This little yellow point in the hose is moving up and down in simple harmonic motion, which is to say that its acceleration is proportional to its displacement from equilibrium. In this case, the equilibrium position for this little point in the hose is just where it was sitting at before the pulses moved through it. So just wherever it was at rest before it started getting shaken up and down. It's hard to see it, but you'll note that as it gets closer to equilibrium, it moves faster and then slows down as it reaches displacement here and here, just like the spring block system does. So every point in the wave, every point in this hose here is doing the same thing. It's acting like its own spring block system. A sinusoidal wave, if you work with the wave function, it's hard to show it on a graph, right? But there's a term for time, because the whole sinusoidal wave pattern is moving to the right or to the left over time. So sometimes zero, it's further along the left, but the later time it moves in one direction or the other, which is exactly what you see in the figure, right? You see the curves here, the pulses, the peaks moving to the right. And this idea of wavelength that we talked about, we haven't talked about wavelength yet because the spring block system is just one point. But at this point, there's like an entire medium that's being disturbed. So now we can properly talk about wavelength, which is just the distance between two pulses. And in this case, we're looking at a still frame of a wave. So this is your hose. If you were to freeze time as pulses pass through the hose, this is what you'd see. Just kind of like sinusoidal shape frozen in time. And you measure the distance between two peaks or any two consecutive points on this graph here, you will get the total wavelength. Now, you can also look at the position versus time graph of a single point. Each point is completing a cycle, right? It's moving up and then back down cyclically. However long that takes is the period of the whole wave. It's also analogously, you can think of the period of the whole wave as how long it takes for two consecutive peaks to pass the same point. So a peak passes the point here, however long it takes for the next peak to pass, that's a period, which is the same as however long it takes this point to move up and then all the way back down. So you can also measure the frequency of the wave, which is if the period asks how long it takes for one cycle to be complete, the frequency is the inverse. It asks how many cycles can be complete in some unit of time. So wavelength, again, is the distance traveled by the wavelength during one period. It's the length of one full wave. You can measure the distance between two peaks. And then frequency is how many cycles are completed in unit time, which is related to the period, which is how long one cycle lasts. With these two properties, then, you can almost define an entire wave because you know how long it is, that's the wavelength, and how fast it moves, that's frequency. You also need to know how far the medium gets stretched up and down, how much it gets displaced, that's your amplitude. So knowing all those things, you can now create the wave function for a sinusoidal wave, where the function tells you the vertical position of any point on the medium by specifying the position of the point using x and specifying what point in time using t. There's one more term in the formula you'll note that accounts for, again, your initial conditions. So wherever you're at x equals to 0, t is equal to 0, the phase factor phi will adjust it to make sure that you match your starting condition. That's necessary. So if y is 0, then your phase factor is going to be 0 because that means you're at 0 displacement. So if you look at the wave function, then there's about 3 terms, right? There's 3 key terms in the inside, which is a term here that specifies the position along the wave. And that is, again, x, the actual position, and then k, which is your wave number, which is related to the wavelength. There's a term here that accounts for the time that has the angular frequency. And lastly, there's the phase shift formula that's related to your starting conditions. And just remember that the frequency and wavelength have the opposite relationship with the two terms. So the wave number k is 2 pi over the wavelength, but the frequency, the angular frequency is 2 pi times the linear frequency. So don't get them mixed up. And Google Slides is blocking it, but there's always the wave speed then is actually the product of the frequency of the waves and their wavelength, which is actually a property of the medium. So the speed's constant. If you increase the wavelength, you must decrease the frequency must decrease, which makes sense because the longer the waves are, the more it takes for one cycle to complete. Note that since lambda is equal to 2 pi over the wave number, and that f is equal to omega over 2 pi, you can also write the wave speed, therefore, as your frequency, your angular frequency over your wave number. Okay. So when the medium is a string, you can actually know what the speed of any wave will be in that string if you know the tension and cylinder mass density. The more tense it is, it's like a more tense string. It wants to go back to equilibrium faster, so that causes a faster motion. But the heavier it is, the harder it is to move, so it goes more slowly. So hence tension over linear mass. Okay, so what happens though if you, maybe you're at the gym, you tie a rope to a wall and you swing the rope up and down. When the pulse hits the wall, a fixed boundary like that, it gets reflected back to you upside down. So when it's like, again, when it's like nailed to the wall at one end, it'll get reflected back upside down. If it's not nailed to a wall, if there's like a hook here, it'll actually swing up and then back down and send the pulse in the opposite direction, but not inverted. So that's a free end. And here, the top GIF is showing you what happens when there's a wall at the end, and the bottom GIF is showing you what happens when it's free to move at the end. So you see how the wave gets sent back upside down, and in the free end, it gets sent back the right side up. Now, the question is, why does the wave reflect in the first place? Well, because it's unable to move on. It can't transmit energy beyond this point, so the energy, has to go somewhere, so it just goes back the way it came. But still, though, there's cases where the waves can transfer from one medium to another. When that happens, you can have two different outcomes. No matter what, though, if you have two mediums connected, like two ropes, you shake the rope, the pulse will get passed on to the other rope, the other medium, but it's also going to get a little bit reflected. Part of the wave will get reflected back. And reflection can happen the right side up or upside down. What that gets determined by is whether or not the new medium is more dense than the first one. So if you got like a heavy rope and you're passing a pulse to a thinner rope, then the wave's going to keep passing on to the thinner rope, but a little bit of that's going to get reflected the right side up back down your thick rope. So you can see that on the GIF here. Now, if you have a tiny little thin wiry rope and you're sending a pulse down to a thicker rope, it's going to transmit, but part of it's going to get reflected back. But this time it's going to be upside down, just like when a wave in a string hits a wall, a fixed end. So if you go from dense to less dense, you get a little bit reflected back the right side up. But if you go from less dense to more dense, you get reflected upside down, but some of it gets transmitted. Also note the speed, hey? It's moving faster in the lighter medium than the heavy one, which makes sense because the heavier you are, the lower your wave speed. And right, so we talked about the fact that waves must carry energy. After all, they can lift a block. If you send a pulse down the string, there's a block attached to it, the block's going to lift up. So it must be giving you some energy. The energy is proportional to the mass of the string, I mean, which makes sense, right? It's like kinetic energy is equal to 1/2 mv squared. But rather than having mv squared, you have mu omega squared and plus the times the amplitude squared of the string. Since right, you have to shake a lot harder to get a taller, bigger amplitude, right? You have to give more energy to the string to get it to move higher. And if it's right, and also the speed of the string, the speed of the wave on the string also gives you more power, also gives you more energy. So here's just kind of showing you how you can think, right, it makes sense to talk more about the power that the wave delivers than say the total energy, because the wave's a continuous propagation of energy. So it's easier to just say, okay, over one cycle, how much energy is being given. It's kind of like electricity, right? You have a constant current of electricity coming your way, so it's better to measure the current than the total amount. Okay, which time do we have? Oh, lots of time. Okay. Does anyone have any questions or wondering about from the last two chapters we just talked about? Okay, I'm just gonna go get more water. Be right back. But yeah, if you have any more questions, just think about it. You can also just send them in the chat. I'll be happy to answer them. All right. So now that we established the basic definition for waves, we can go ahead and talk about very particular case, which we deal with all the time, which is sound.
Sir,
Yep.
like in like the the chat room has like a question for you. Someone in the chat posted a question.
That's a question in the chat. Oh, okay. Okay, thank you. So, phase constant. Yeah, so why will the phase constant now be 0? Well, that's a good question. So let's have a look. Let me pull up the whiteboard. So, in the case of a wave, we're looking at a wave's function, omega t. Right, to find the phase constant, we start with the wave function. And if we look at our wave as in a graph of its horizontal position versus its vertical displacement, so we fix it at a point in time. So here, right here at the origin, is your point x is equal to 0. So if we specify this particular point at this particular time in the formula, what we're left with is the amplitude times cos, and then the phase factor. So what this is saying is that, right, the phase factor must be some volume, must be some angle, such that at this particular position, at this particular time, you get the starting vertical position, right? So we know, right, that at this point y is equal to 0. That means then that the formula gives you 0, right? That's saying that a cos phi is equal to 0. So in this case, your phase factor must be something that agrees with that, something that makes cos is equal to 0, right? You'd have a value of pi over 2 as a potential phase factor. Okay, yeah, so somebody asked, yeah, the formula sheet I gave you, there's a typo there where like you see sine and cos be repeated. I don't know why that happened when I hit the print button, made the clone, but yeah, anyways, the formula sheet has sine and cos show up twice per formula. Don't worry about that. There's going to be one sine there and one cos. But they'll be corrected once you get the actual formula sheet in your as part of the midterm on Wednesday. Now, if the wave were to, if you know for a fact that like the wave, rather than starting at y is equal to 0, say that the wave starts at y is equal to the amplitude, then that means that the initial condition changes. Your initial condition is that now y is equal to a at t0 and x0. And in that case, then a cos phi is equal to the amplitude, which means that cos phi must be equal to 1, must be maximum. So phi can only have a value of whatever makes cos equal to 1. So it could be 0 or it could be 2 pi. But say, for example, that let's make this, let's actually know, let's say we actually know the amplitude of the wave. Let's say the wave goes to an amplitude of, holy moly. That started looking really nice until Zoom decided to throw up my drawing. Okay, let's say that the max amplitude of this wave is 2 meters. Let's make it 4 meters. And at this point here, x equal to 0, we are at 2 meters. In other words, we know that at t is equal to 0, x is equal to 0, our amplitude is at 2 meters. Which means that then that 2 meters or amplitude times cos phi has to give us, sorry, the amplitude is 4 meters. So the amplitude term should be 4, should give us 2 meters. In other words, cos phi needs to give us one half. So if you solve for that, right, you get a phase factor in your calculator, you get a phase factor of about 60 degrees, pi over 3. So then your wave function, right, will be 4 meters cos whatever your angular and wave number are, plus pi over 3. Now, suppose that your wave actually looks like this, and your starting condition is negative -1 meter. Then you'll end up with 4 meters cos phi is equal to -1. So you get cos phi is -1/4. And in that case, again, it's the same algebra to get the angle. And then your phase factor would be something like something close to 180 degrees. Off the top of my head, or like, I want to say like 170 degrees. So inverse cos -1/4. That will be about 104 degrees. Cool. So then your wave function, right, would be then in this case would be 4 meters cos kx plus omega t plus 104 degrees. In radians, that would be times pi divided by 360 would give you Yeah, it's funny. Oh, there it is. I was going to find the pi button. So in radians, you want to have the answer in radians. So I'm just converting 104 degrees to radians. That's 1.82 radians. And having this phase factor here would ensure that your wave function actually looks like this, that it starts at -1, right? Because you plug this back in and you get -1, like the graph suggests. So that's how you find the phase factor, and that's what it's for. You can also think of the phase factor as essentially a horizontal shift. So it aligns your wave so that the correct part of the wave falls right on the origin at time 0.
Awesome. Thank you, sir.
No worries. Okay. All right. Yeah, so this is the best picture in the entire textbook. Just gonna take a second to appreciate the dog looking at the phonogram. Amazing. Right, okay, so sound waves. Yeah, it's basically disturbance in the air. When we talk, we're just making our mouth make the air vibrate, and the people listening to us, their ears receive the vibration from our mouths, and our brains register those vibrations into different sounds, and those sounds make words and sentences, and that's how we communicate, by vibrating sound with our mouths. Anyways, the biggest takeaway from longitudinal waves is the fact that you no longer have a medium that's wiggling up and down as a wave shoots through it, but rather you have a medium that's now compressing and expanding as the pulses move right through in the same direction. So this is better shown than said, but just remember that, well, in a wave on a string, you had these peaks and these troughs. For the longitudinal wave, you now have this point where the particles are kind of compressed together, and this is kind of like a peak. Then you also have these points of where the particles are more stretched apart, creating an area of lower density. This is called rarefaction. So peaks and troughs for transverse waves, compression and rarefaction for longitudinal waves. So how do we describe the waves in this time where there's no longer a vertical displacement, but rather a displacement along the propagation? You set up a wave function that looks a lot like the It looks a lot like the transverse wave function, but now it's for the displacement of any point in the medium. You can also, rather than talking about the displacement of the particles in the medium, you can talk about the pressure variations in the medium, since after all, as the particles displace, they create points of more and less pressure. So these are two graphs showing you the same sound wave, but on the left, it's being described in terms of its variation in pressure, and on the right, it's being described in terms of the displacement of the particles. Whichever one you use, they're both descriptions of the same sound wave. The pressure description, right, is a little bit out of phase with the displacement one, because the displacement one is telling you how much each part of the medium displaces. Because of that, right, this part of the medium right here is displacing all the way to this area over here. So it's sandwiching these particles here, but the particles here themselves don't move all that much. So if you look in the displacement graph, it's telling you that the particles at the very beginning of the wave get displaced the most, all the way to this area here. Well, the ones that get sandwiched, which are the ones right here, are kind of standing still. They get smushed by these particles here, displacing to the right, and they get smushed by these particles here, displacing to the left. So if you were to look at the wave then in terms of pressure, what's happening is that wherever the particles get sandwiched like this, the pressure variation is increasing. So at this point of max smooching, you have a high pressure point. But also there's points then where rather than the particles getting sandwiched, it gets spread apart. So there's lower pressure in that area compared to anywhere else in the medium. So these are low pressure points. But the reason why they're low pressure points is because all the particles in this area have displaced one way or the other. So the medium's at a maximum displacement in this area because the medium has moved quite a lot, leaving you with a low pressure area. So delta P here, when we say pressure variations, that's what delta P means. It's not an absolute change in the pressure, but rather it's a relative change in the pressure of the medium. But remember, waves travel with time. So this is just a snapshot. Over time, everything's moving to the right. So these areas of sandwiched particles and spread out particles, this whole thing's traveling in sequence to the right, like on a conveyor belt. Here we go. Here's the gist. So again, big shout out to Flipping Physics for making the most incredible GIFs that really show what's happening. Waves are by nature propagations in time, so you gotta show them in motion. So all the black circles here, little black dots, they're the air particles. And you see how this sandwiching of the particles creates high pressure areas, and they just keep getting sent to the right. So if you graph pressure on the y-axis like you do at the bottom, you see how it looks like a sinusoidal wave, even though it's not a sinusoidal wave physically, it's a transverse wave. But it's still the same idea. You have this points of compression being sent to the right, and in between each point of compression, right, there's these points of low pressure, there's these points of refraction right in the middle. So you can kind of know that here's like between two compression points, right in the middle between them, there's these areas of like where the points are really far apart. These are your troughs, these are your rarefactions. Unlike waves on a string that just move along the string, once you start disturbing the air, like I did, I guess hitting my hand against my other hand, air, right, it's like a three-dimensional medium, so the sound waves that you create when you make a sound go out in all directions. Still, a wave is a wave, so its speed is a property of the medium, in this case, the air in the room, And it's always going to be related to the period, sorry, to the frequency of the wave times its wavelength. And in 3D space, then you can think of a sound wave as a series of ripples. And again, right, there's a consecutive number of compression points and rarefactions, compression, rarefaction. You can always then measure the wavelength by the distance between two compression points. So if I go back to the GIF, the distance between this red line and this red line is the wavelength. And however long it takes for like the time between one red line and the next red line passing the same point, that's a period. One full cycle is two compression points passing the same point. So yeah, so speed's constant. Here is a speaker system. The top has a smaller opening. So what it'll end up doing is it'll send out high frequency waves. And since it's the same medium, that means that to compensate, the wavelength is smaller. Well, the bottom sends smaller frequency waves, which means they have a long wavelength. This is called a woofer. So it kind of plays the lower frequency sounds in your system, while the top part plays the higher frequency sound. So it splits the sound in two. So it's right, you get better sound quality when different parts of the music are assigned to different channels. So there's also the subwoofer, which plays like the bassier notes in a song. That plays the even smaller frequency sounds, you know, the boom, 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 boom part of the song. Right. So if you actually want to know the speed of a sound wave in any medium, you need to know, how stiff the medium is and how dense it is. For gases, that comes down to a ratio of what's called the bulk modulus over its density. The bulk modulus, just need to know that essentially is how it's basically a measure of stiffness, but for gases. So that's a rule of thumb. The hotter it gets, the faster sound moves in air. Because if you remember the formula, it's the modulus over the density of air, right? So as air gets hotter, the density drops, which makes things move faster. So it's just a rule of thumb. The hotter it is, the faster sound moves. I had a picture of thunder here and lightning because assuming, right, we're at like a room temperature, the speed of sound in air is about 340 meters per second, which means that it moves 1 kilometer, sound moves 1 kilometer per 3 seconds. So if you see lightning and 3 seconds later you hear thunder, that means that the lightning struck 1 kilometer away. If you see lightning and hear thunder 1 second later, lightning is about 350 meters away from you. You should probably run for cover. Fun fact, statistically speaking, golf is the most lethal sport. The number of deaths in golf is higher than any other sport due to the number of people who have played golf in thunderstorms. That's not going to be in the midterm, but just a fun fact. So remember how we talked about transverse waves having energy that they carry? The propagation of energy, after all, that's a wave by definition. Well, we're going to talk about that with sound waves as well, since being waves, they must be carrying energy outwards. When I clap my hands, the sound, the waves that vibrate, that bring that sound to your ears, are carrying energy. But they're also like a ripple propagating outwards. So what you get to hear is just a small part of that ripple. So rather than talking about the total energy coming out of my hands, it makes more sense to talk about how much energy is received. So that is your intensity. It's how much energy you're receiving from a sound wave. And the rule of thumb is that the closer you are to the sound source, the more intense the wave is, since you're kind of getting hit with a bigger part of that ripple. right? If you're like a Marty McFly here, you're playing too close to your speaker, you're gonna get blasted away. But if you stand farther away from the speakers, like in a concert, you're gonna, get less sound to your ears, which will save you, from hearing problems later on in life. So how do we actually measure intensity of a wave? Well, it's just a measure of how much energy the wave's delivering, the power, and over the area. So the area there is just to account for how much this ripple of sound has spread out by. It accounts for the fact that the farther away you are from the wave, the less energy your ears receive, the less intense the wave is. So the rule of thumb is the farther away you are, the less intense the wave is. And the intensity is also measured. Since if you look at a single cycle, the amount of energy that each part of the medium is passing through inside the cycle is not constant, but overall the total energy per cycle is constant. So that's why the intensity is measured in terms of the average power per cycle. It doesn't really affect the calculations, just an understanding that energy does fluctuate within a cycle. So you just look at the average amount of energy. Now, because you can also talk about the energy of a wave in terms of its speed and amplitude, you can rewrite the intensity formula in terms of the way that the pressure variation occurs. So this formula here, right, may be reminiscent of the one you've seen for transverse waves, but you don't have an amplitude. Your amplitude term is now your P max term, or the max displacement term here, since that's related to the energy. So biggest takeaway, the most simple scenario, if you just model whatever's making sound as a point source, so just a point in space emitting sound in all directions, then you can think of it then as the sound creating these ripples throughout all space that are just coming out of it. Then each ripple is kind of like a sphere. It's kind of like a sphere that's growing, like you're blowing a bubble with bubble gum. The farther away you are, though, you get hit by a relatively smaller section of that whole ripple. So you can then model the intensity as a fraction of the total power that the source is producing divided by the total surface area of the ripples. And because the farther away you are, the bigger the ripple is, the surface area only gets bigger and bigger, which means that the energy per unit area in the ripple drops. The closer you are to the source, you get hit by a bigger chunk of the ripple, so you get more energy at you. But the farther away you are, the ripple's so big, you only get hit by a relatively smaller part, so the wave sounds less intense. But you can kind of see here how, like, if you're standing here, you get hit by the wave front. It's quite concentrated. But you're standing over here, the wave front is diluted. It's spread out over a bigger area, so you're hit with less energy. So the rule of thumb is that there's an inverse square relationship between the distance to the source and the intensity. If the intensity is equal to 1 when you're at distance r from the source, if you double your distance, the intensity is going to drop by a factor of 4. Or if you're 2 meters away and you say you're like, I don't know, 50 meters away from someone playing music. If you walk halfway through, you're 25 meters away now, the intensity of their sound is going to be 4 times bigger. Or maybe you're 10 meters away from your friend playing guitar and they start playing Wonderwall, so you kind of get sick of it and walk away. By the time you're 30 meters away, the intensity of Wonderwall has decreased by a factor of 9 because you increase your distance by a factor of 3. So your intensity drops by r squared. So 3 squared is 9, drops by a factor of 9. So Don't forget the inverse square relationship. Anyway, so yeah, intensity can be thought of as a way that we perceive sound. The more intense a sound is, the louder it is. But the intensity of the sounds that we can actually hear have a big range. So rather than talking about a range that spans, thousands and millions of units, instead we talk about the sound level scale, which is in decibels, which is more reasonable for comparing noise. So the decibel is just a conversion of the intensity of any sound. You take it by taking a logarithm of the taking a logarithm of the intensity level. I thought I dropped something. And basically, because you're taking logarithms, it kind of shrinks down all the intensities to a much smaller number. So they can be compared on a scale that's from, say, like around 1 to 100 rather than 0 to 1,000,000. So kind of to show that in terms of sound level, in terms of intensity, a jet plane is like 10, 100 million times louder than a whisper. But sound level is much more sensible, that you can compare sounds in a much smaller scale. Oh, also the sound level formula, right, has a term at the bottom here. This one accounts for the threshold of hearing. So it's built into the function because anything below this threshold, we can't hear it. So it'll just be a 0 since we can't hear it anyway, so we don't worry about that. The human ear can actually pick up some sounds that are very quiet if the frequency is close to the natural frequency of the ear. So around the sounds that are like about 1,000 hertz in frequency can be heard even if they're really quiet, up to a point that it sounds too quiet, then you can't hear it at all. However, no matter what the frequency of sound is, if it's too intense, then we'll just feel pain no matter the frequency. And that's the threshold of pain, which is the line here on above the white area. Okay, still good time. Okay, the last thing we talked about in this chapter is the Doppler effect. So that's when sounds sound like higher or lower pitched as things move away and towards each other. So when a car passes by you, it sounds like it's louder. Drives away from you, it sounds quieter. So basically, something emitting sound with a particular frequency, to the observer, the frequency will appear shifted if you and or the source of the sound are moving. If you're moving towards the source and the source is moving towards you, the frequency is higher because the waves are hitting you faster. If you're moving away from each other, the frequency is lower. If one's moving towards the other and one's moving away from the other, the frequency might increase or decrease depending on which one's doing their job faster. So if a car is moving towards you, it's emitting sound waves, and the crests are bunching up in your direction. So it appears they're hitting you faster than they're being emitted. That's why you hear a higher pitch, a higher frequency. If you're standing on the other side, though, the waves are coming farther and farther away, so they're catching up to you. The same thing would happen if you try to run away from the car. The waves will have to catch up to you, so the frequency you hear is lower. If you run towards a car, they will hit you faster, increasing the perceived frequency. Oh, yeah. If you break the speed of sound, if you move faster than sound, you'll outrun your own ripples, essentially creating this huge wavefront in like a cone shape that expands outwards and has a lot of energy on the edge. This is called a shock wave, and the faster you move, the narrower the shock wave. So got a question on the formula sheet. So other than that weird sign typo, the formula sheet is final. Everything you see there for all the questions provided. Like I may have said to some of you, there's one question where you'll be asked to derive the formula, but it'll be very clear what needs to be derived. Like it'll talk you through the process. Okay, last chapter we did superposition. So basically, what happens when two waves meet? They just pass each other and they keep going their own way. When they overlap, though, their amplitudes combine. So in this case, they'll meet, make a big, tall bump, and then just keep going through each other. So to do this mathematically, actually, when you have two waves in the same medium, the combined wave is just the sum of the two wave functions. So in the real world, it's not so simple combining waves, but for this sort of ideal physics scenarios, we'll just assume the superposition principle holds to its fullest, or like waves are just linear sums of simpler waves, and they can be described if you know the wave functions. So again, here's another drawing. There's two waves, they meet for a few moments, they overlap when they occupy the same space, and then they keep going. So this is what makes waves different from objects. If you recall the bumper carts example, bumper carts cannot occupy the same space. If you run against each other, they're going to collide and bump off. Waves, though, can overlap with no problem, just keep going past each other. So if the waves are actually overlap in a way that the resulting wave is actually taller, that they build up on each other, then that's called constructive interference. Like the word construction means, you're piling bricks, making a building taller. However, pulses can also be upside down in the case of a transverse wave. In this case, the overlap of the two waves, the resultant wave, is overall shorter than either wave. So that's destructive interference. That's caused when the displacement of the pulses overlapping are in opposite directions, right? In this case, one's up, one's down. And right, like destructive, right, like tearing something down, it's making it smaller, like it's happening when pulses come in and out of phase. So here's a GIF of constructive interference. Pulses come in at the same time, they build up to make a taller pulse and then keep going. But here they're out of phase. So when they meet, right, they briefly make the hose go flat, and then they keep moving through. But right, for like that moment where they meet, the resulting wave is shorter than either one. Here's destructive interference, but frozen in time, just showing you 3 different snapshots when they come to each other, when they meet, and then when they just keep passing through like nothing happened. So with the superposition principle, you can then, if you know the two wave formulas for the waves that are combining, then the resulting wave will look like this here. And the biggest takeaway from this is just that there's a maximum possible amplitude you can get. If the waves are interfering completely constructively, then the wave will be twice their amplitude. Or it can be completely flat if they're destructive interference. So depending on how they are in phase or out of phase with each other, the resulting wave, the green wave, will either be taller or shorter. So in this case, you can't see the two waves because they're overlapping, but the two waves have the same phase. So the resulting wave has twice the amplitude. And in the combined formula, right, there's this term here, the 2a cos phi over 2. This accounts for the potential amplitude of the combined wave. When they're in phase, this term is maximized, so the total amplitude is 2a. This term over here, then, this just describes the motion of the wave as it was any other wave, right? Wave number, angular frequency, and phase shift. So if two waves overlap again in such a way that they're exactly half a wave out of phase, or in terms of phase would be half a cycle, so that will be pi radians out of phase, then that means that the peaks are aligned with the troughs. In other words, the superposition gives you a flat line. So that's distracting interference. Now, you've seen that with the pulses that came through and became flat for a bit and then kept moving. The wave actually has, the two waves have equal amplitude, but they're opposite, they're flipped. Then the resulting wave is just flat. If one's taller than the other, the wave will be short, but not completely flat, since there's still some net amplitude. Now, there's also the in-between case, where the waves are not either completely out of phase or completely in phase with each other, and that's just called interference. So here, the resulting wave is the red one, and you can kind of see how it's not quite twice the amplitude, but it's not completely flat either. So another way to determine whether the waves will interfere constructively or deconstructively is when you have two waves coming from different sources, so like two speakers, and if the waves meet you and they're in phase when they meet you, then that's good. They're gonna do constructive interference. If they meet you and they're out of phase with each other, it's gonna be destructive interference. So for sound waves, there's two speakers and the waves from one come out of phase with the waves of the other, it's gonna sound quieter because they're destroying each other. But the two speakers come at you and the sound waves are overlapping in phase, then you're gonna hear a much louder sound, because the waves are overlapping constructively, which means that the resulting wave has twice their amplitude. And for sound waves, amplitude, which is, well, in the case of a sound wave, it's actually the pressure variations. If that's big, that corresponds to a much louder sound, because remember, the intensity is proportional to the pressure variation. So when they're in phase, resulting sound wave has a big pressure variation, which means it's a much more intense wave. If they're out of phase, it's a quieter wave. Another way to think about them being in phase is that you can think about the paths that they travel to get to your ears. So if two waves travel a path such that the path difference is equal to a wavelength, they'll arrive in phase, because that just means that one had to travel, one full cycle of a wave to get to you. It's still arriving in phase, because after traveling one extra cycle, it's starting a new cycle. That also means, though, that if one travels an extra half wavelength, then it'll arrive out of phase with the other. So for constructive interference, the path difference must be a multiple of the full wavelength. For destructive interference, you must be an odd multiple of half a wavelength. Anywhere in between, you just get some interference, but not destructive or constructive. So here's showing you what I'm talking about. Two speakers, here are the wavefronts. And the points are points of constructive interference, because if you're standing here, right, the troughs are overlapping, here the rarefactions are overlapping, so they're in phase in these points. Here's showing you two speakers again, but the blue points are constructive interference, so are the red points. So whether crests, when the two crests align or two rarefactions align, that's constructive interference. When a crest of one aligns with a trough of the other, or a compression or rarefaction, because they're sound waves, when that happens, that means they're out of phase, right? When you have like this aligns with this, it's destructive. But when you have this aligned with that, it's constructive. Same when you have like a trough aligned with a trough, it's also constructive. So you can kind of see then the black points are the distracted points, because over here, if you look at this one here, the speaker at the bottom, this is a trough for the speaker at the bottom, but from the speaker at the top, this point here is sorry, I go the other way around. For the speaker at the bottom, this point here is a peak. It's a point of max compression. But for the speaker at the top, this point here is over here is a rarefaction, a point of minimum compression. So you have a rarefaction of one speaker overlapping with a compression of the second speaker. That creates superposition, just makes a flat wave. So that's destructive interference. Here's a graphical representation of the path length, where you have, this is the point where the listener stands. This is how far the wave travels from the first speaker. This is how far the wave travels from the second speaker. So the path difference is the difference between the two. And here's just showing you the different initial conditions. And basically, it's telling you that, okay, one wave travels an extra distance equal to a wavelength. That's still okay because they'll be in phase. If you travel the distance equal to half a wavelength, then the two waves now will destroy each other. And if it's somewhere in between, they won't destroy or fully overlap each other. There'll be some interference in the middle. Anyhow, took too long for this. Okay, so standing waves. To create standing waves, you just need a wave and its reflection overlapping constantly. So by reflection, I mean it's the same wave, everything's the same, just moving in the other direction. So the wave here and the reflection here overlapping. The resulting wave then is a standing wave. And what that looks like is a wave that doesn't seem to move. So here you see the blue wave and its reflection, the red wave, creating the standing wave. So what you actually see is the black wave here. And note that it's not moving. The whole medium is oscillating except for certain points, but it's not moving left or right, just oscillating up and down. So there's a wave function for this. The first term, which uses a sine function, this one is sort of for the specifying a point in the medium, because you'll note that there's points in the medium that displays the most. There's points that displays the least, like this point over here, and then everything between displays by some amount. So that's what the sine term accounts for. The cos term is just there for timing, right? It just accounts for the fact that over time, the standing wave jiggles up and down forever. The biggest takeaway, though, from the standing wave is the points of max displacement being called antinodes, and the points where the wave doesn't displace at all are called nodes. Nodes, remember, like point of no displacement. Fun fact is that no matter how big the wave is, an antinode next to a node will be a quarter of a wavelength away. From one node to another, the distance is half a wavelength. Same with an antinode and its next antinode. Note that in a standing wave, a full wavelength kind of looks like two lentils next to each other. So this is a full wave. And over time, like a skipping rope, it'll swing down, it'll swing back up. And this part here swings up and down cyclically. So then over a whole cycle, the standing wave goes from this to that and back to this, which means that there'll be a point where the whole wave looks flat. The wave goes flat every half. So remember how you pass equilibrium every half period? Well, for standing waves, you go completely flat every half period. If you start off with, if you start off with your standing wave initially being fully stretched out, then it'll take a quarter of the cycle to go flat, half the cycle to be inverted, 3/4 of the cycle to go flat again, and then the full cycle to be back to where you started. In case we get kicked out of the meeting, you should know how harmonics look like. So you should know the first 3 harmonics of a string. So there's always going to be 2 notes at either end. And you should know the first 3 harmonics of the pipe open at both ends and the pipe closed